Okay, on to the second part of this problem. This time we're looking at systems here. So for the very first case, it says the forces on the system of the 2,000 kilogram and 3,000 kilogram cars. So we're going to draw ourselves a little system right here that includes the 3,000 and the 2,000 kilogram cars. So I've boxed them in here in this case. Remember, just like from before, we can find the weight of something or the force of gravity on it by using weight equals mass times gravity there. And also remember, last time I used 1 square is 3,000 newtons. The numbers get a little bit bigger this time. Again, I already worked all the way through it, so I have some foresight here. But I'm going to say 1 square is 6,000 newtons on this diagram. So what are the forces on here? Well, first of all, we got the force of gravity. We've got 3,000 and 2,000 kilograms. So the total mass of this system here is 5,000 kilograms. And if we plug that into our weight equation, 5,000 times 10 is 50,000 newtons. Now it's 6 squares per, or 1 square being 6,000 newtons, then to get to 50,000, that's about 8.33 squares roughly. So 1, 2, 3, 4, 5, 6, 7, 8, 3, there-ish. All right, so let's call this the force of gravity. And then 1, 2, 3, 4, 5, 6, 7, 8, and a third-ish. Let's call this one the normal. So normal up, Fg down there, and then we are going to need a force that pulls everything forward. We know it's moving forward. There has to be an outside force. What is it? It's right here. It's F2. And so we actually solved for F2 on the previous video, and in that case, F2 equaled 10,000 newtons. So at 6 squares a piece here, it's just over a square there. So let's call that F2. Now what about F3? You might say like, well, where's F3 go? F3 is an internal force. It's inside the system, so it does not affect the system of the 3,000 and 2,000 kilogram cars there. So when we go to set up our little equation right here, we can say there's the force of F2, and then that's going to be equal to the mass times the acceleration. The mass in question here is actually mass 1 and mass 2. And so both of those are inside the system and get accelerated there. So let's look at the next system that they have here. This time they say the system is the 2,000 and the 1,000, so these two cars. So let's add those two together in a system here. I notice they're sort of overlapping, but that's okay. So now these two cars are in the system. They've got a mass of 2,000 and 1,000, so all together they have a mass of 3,000 kilograms. If I plug that into the equation up here, I get 3,000 times 10 is 30,000, and 30,000 newtons is the weight then, which would be 5 squares. 1, 2, 3, 4, 5. So I will call this one here the force of gravity. I know I've got the normal force up. It's got to be the same length to balance it out because there's no acceleration in the y. 1, 2, 3, 4, 5 up. So that is going to be the normal force there. We can see right here that we have force 1 accelerating that system forward, and we solved for force 1 on the previous page there. Force 1 was 12,000 newtons, and so we can put that forward. That will be 2 squares. But we also, inside here you may say, well, what about F2? F2's not there because it's an internal force. It's within the system. But F3 is pulling back there. And so we do have F3 going back, and F3 was only 6,000 newtons, so it's just 1 square now, one tiny little square, and I'll label that F3 going back like that. So finally, last system that they have here, it is all 3 cars are in the system. So let's add those 3 cars into the system right here. What is the mass of the entire system? 3,000 plus 2,000 plus 1,000 is a total of 6,000 kilograms. If we plug it into our equation here, 6,000 times g which is 10, would be 60,000 newtons. And so that's 10 squares down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All the way to the bottom there. So Fg here, and the normal force up would also be 10. And I'm looking over here and realizing I forgot to write the equation. So let's pause for a moment and do that. What is the equation here? On this side go the sum of the forces. We have F1 pulling us forward, and we have F3 pulling us backwards. The mass part of MA is the mass of the system we're talking about. In this case here, it was the 2,000 and the 1,000. I'll just call them M 1,000. I'll call it M1 and M2 here. And I realize another mistake here. If I call this mass 1 and this mass 2 and this mass 3, then this over here should be mass 3 plus mass 2. So, there. That's the equations on that side. Now, what forces do we have horizontally? Well, F3 and F2 are both inside the system there. And so they don't count. You only have F1. We solved for F1 before. It was 12,000 newtons, so it will be 2 squares on here. But there will be no backwards force on the system itself there because there's no friction or anything like that. And the F2 and the F3 are both external forces. We already figured out on the backside, they say, what are the forces F1, F2, and F3? We already figured those out as 12,000, 10,000, and 6,000 newtons in the previous video. The last thing is the question there that says, without doing any of this complex math, how can you know that F1's got to be the most, and F2's got to be the middle amount of force, and F3's got to be the least? That's because think about what F1's responsible for pulling. All of this mass. All of that mass there. And so F1 is responsible for pulling 6,000 kilograms of mass. If we think about F2, it's responsible for pulling these. So F2 is responsible for pulling 5,000 kilograms of mass. And then F3 is just pulling this last car here. So F3 is pulling 3,000 kilograms of mass. So we know that F1 has got to be the biggest force. Everything's accelerating the same, 2 meters per second squared. And again, F1 is pulling all of this here. Imagine, sometimes people say like, well, F1 is only pulling that guy, but it's pulling all of these. Imagine like you're hanging from a cliff here, and you've got one person hanging off the cliff, and they've got a person hanging on their arm, and they've got a person hanging on their arm. Then I think it's easier to see that this person is holding up everybody. And this person here is holding up themselves and this person. And it's only this person that are just holding up themselves.